get this thing to, there we go. So I'm going to do sort of three mini presentations in this presentation. The first one is just a brief intro to sea to shore systems. Then I want to do a very quick and dirty talk about sound in the ocean. I normally give like a 1 hour, 2 hour, 4 hour introduction to sound in the sea, so that you're only going to get a couple of little bites of this, but hopefully it'll be fun. And then I want to do a little bit of a presentation on the BC Coastwide Hydrophone Network and give you a feel for some of the work that's going on along the whole coast. And there's way more going on the whole coast than just the BC Hydrophone Network. We have a lot of different clients, and then there's all the DFO hydrophones, the Transport Canada hydrophones, and the Ocean Network hydrophones. Ocean Networks Canada hydrophones. So there's a lot of hydrophones on this coast. I think it must be one of the most wired coastlines in the world. Okay, so sea to shore systems, it's primarily just Jeff and I, although we have hired students in the past. It's not really fair to call Joel a student. He's been working for many years, and he came basically hitting the ground running. But primarily it's just Jeff and I. So Jeff does the executive stuff and the electrical engineering, and I do the science, sort of the physics and the underwater acoustics, as well as the mechanical engineering. Our core competencies at the moment, although this will expand later, but really are cabled to shore acoustic systems. We also do underwater cable assemblies for people on contract, like Parks Canada, for example. And then there's oceanographic sensors, which, as Matt and many of the other people here that used to work at AML Oceanographic know, that we've been involved in that for many, many years. So in terms of our services and products for our company, it really focuses primarily around cable to shore acoustic systems for both products and services. But on the services side, we help our clients do site selection. And also, once we've selected a bunch of different possibilities by looking at all of the underwater bathymetry for acoustic propagation in the areas, then we'll go out and do site surveys and see if it'll actually work. In some cases, we use an ROV for that. And we have used divers as well as little hand-deployed cameras, but the ROV is much better. We also do system design for a whole bunch of our clients, and every client has different needs, and so the systems have to be tailored to each of the client's requirements. We also do install work and maintenance work on them. As I said before, we do underwater cable splicing for a bunch of different people, and we've also, for a number of different companies, done acoustic noise analysis and vessel analysis from acoustics. And Open Ocean Robotics, to the four of you here, we've worked with your company before as well. On the product side of things, again, cable to shore systems are our main target here, and we do off-grid systems, we do on-grid systems, autonomous logging systems, and radio network systems to bring all the data back to one particular site in real time. We also, maybe I'll talk a little bit about some of these pictures here. So on the left here, we've got Jeff sitting in one of our large boxes. We also have a smaller version of this. And he's doing the final wiring on a system, a shore-based system. So there's a big solar panel array in front of him here. And then we've got a whole bunch of golf cart batteries in the box. And then he's doing up the final wiring for this system. On the seafloor, we have these tripods. And these are foldable tripods, so you can collapse them. We normally do our work from a small boat. So being able to collapse these when you're on the boat, so you can get 2 or 3 of these systems into a boat is really nice. And then we can fold them, clip them together, don't require any tools to do that, and have them ready to throw over the side quite quickly. Here's one that's on the upper picture here. If you can see my mouse, it's partially folded, and the shrouds are over the hydrophones. In this case, there's 2 hydrophones on this particular mooring. And then to get that data up to shore, we have cables. And so you can see me working on some armor for this cable coming in through the intertidal zone here. And there's different things we do to protect these cables, but yeah, armoring is an important factor. And then here's another picture of Jeff here working in one of the labs. Each of the labs is radically different, but you have sort of the same gear. This is an on-grid system. So in the bottom here, we have a bunch of golf cart batteries and a pure sine wave inverter and chargers and stuff. So that this system, if the power goes down on the island, which it always does, this system can keep logging data for a day and a half until the power is brought back up. So we have two computers here. One is logging 2 hydrophones, the other one's logging 2 hydrophones, and then there's a third computer in behind Jeff here, which is the user interface. Because what we don't want to have happen is the users being able to modify the data that we're collecting. So they have read-only access to those big NAS drives. Another of our products is a small boat deployable acoustic recording buoy. So CEDIS is operating one of these buoys right now for monitoring the whale watching fleet. And the Couch and First Nation has just bought another one. So, you know, we haven't built very many of these things yet, but there seems to be a demand. So we're going to have to ramp up on that. But this is a tiny little buoy. It's got batteries inside it. It's got a computer inside it. All you got to do basically is take the flagpole, attach your flag to it, but plug it in the top so you can see this thing. And then you take the 10-meter cable, plug it into the bottom and throw the whole thing over the side. And that way you can take your boat away from the buoy, because boats generate a lot of noise. The slapping of the waves on the boat, people walking on the boat or talking on the boat even can contaminate the noise. So this way you can get away from that buoy and record good quality noise data. And then we do underwater, custom underwater cables for people as well. Okay, so that's our products. For developments, we've got about 15 or 20, I think, projects in our bucket list for doing, but since there's only 2 of us, we don't have much time. So the 3 sort of systems that we're going to focus on in the coming year are an improved version of the low frequency hydrophone calibration system. I developed one for Ocean Networks Canada, which is they're still using. There's a few issues that I wanted to fix with that thing, so I've come up with a brand spanking new design for that, which is a lot easier to operate and a lot more portable for us to take up into the field. So the hardware is done for that, but we still have to do the software. We want to change our folding mooring into a collapsible mooring, and that's something that we'll be building in April. And then that small buoy that we have, we want to upgrade that to a ray so that we can start do direction finding. So you can throw 2 or 3 of these things out in an area that you're visiting, and you can actually track whales. Okay, I'm going to switch gears now and go into underwater sound. So there's a whole whack of different types of energy that you can use to explore the ocean environment around you. Of these various types of energy, sound is by far the best form of energy for exploring the ocean. This little graphic here just shows the different colors of visible light and how far they can penetrate into the ocean. So this is at the equator on the left here, so down a couple hundred meters. And that's because at the equator, there's very little nutrients in the water, and the water's pretty clear. When you get up to where we live, like on the right-hand side here, it's much less penetration. And during the bloom in sort of the May timeframe, you're lucky if you can see 30 centimeters in front of your mask when you're diving, as most of the divers here can attest. So sound is really important, and as a result, most marine life has evolved to take advantage of sound. And all of the vertebrates certainly, and many of the invertebrates too. And for most, it's actually their primary sense. So they don't really use sight as anywhere near as much as they use sound to orient themselves and do their daily life functions in the ocean. So I wanted to give you a couple of examples of local sea life that that use sound, and I've listed a whole bunch of different uses for sound over on the left here, and then some of these local species. And there's many, like many species. I'm only just going to touch on a couple of them. But if you want to turn your speakers up as high as you can go, I'm going to play these sounds. So this is a clip of Pacific white-sided dolphins, and they're the squeaky sound in this clip. And there's some clicks in the background. That's actually a sperm whale. But here's Pacific white-sided dolphin. I hope you guys can hear that. A little bit hard. Crank your speakers as much as you can. Sorry. Okay. The clicking that you heard in that last one was from a sperm whale, and here's a picture of a sperm whale that Jared Towers took. He works for DFO up in Alert Bay. And this particular whale is named Yucasam. It's a young male. And he actually circumnavigated Vancouver Island a couple years ago, which is kind of not unheard of, but it hasn't been heard of in the last sort of 30 years. So pretty unique opportunity. And so this is the sound from this specific whale that Jared recorded. So it's that clicking or banging, those gunshots that is what the whale's using. Now the sperm whales have the largest sonars on the planet by weight, bigger than the military sonars even. And these guys can generate an incredible amount of acoustic energy, so much so that they can stun and sometimes even kill giant squid, which are their prey. But they can also use these things to navigate and see their surroundings, these clicks. And 1/3 of their body length is basically devoted to this sonar system. So it's very, very important. In fact, the clicks that they produce, if you look in detail at the click, you can actually, by looking at the reflections within the head, you can estimate the size of the head, and then you can estimate the length of that whale just from looking at the acoustics of one click. It's really pretty cool. So you can identify the difference between clicks between different whales in a pod just by looking at the length of the animal based on the clicks. Here's another local denizen. So the plain-fin midshipmen. They're called midshipmen because they have a row of little fluorescent spots on their along their sides, kind of like the silvery buttons on the uniform of a UK midshipman or cadet. And these are part of the toadfish family, and they bury themselves during the day. But if you go diving at night, I've been diving in areas where these things come out of the sediment, and there's hundreds of adults just sitting on the bottom, and 1,000 or so juveniles hanging about 1 meter above them in the water. And they generate noise. They have a swim bladder, a little air-filled bladder, and that swim bladder, they have muscles around it so they can vibrate it, and it creates noise. And this is what a single plain-fin midshipman sounds like. It sounds just like 60-cycle transformer hum. And if you get thousands of these things in a bay, you can hear it above water. They're really, really loud. And they use that for attracting mates. Another iconic local species is the humpback whale. So this is a picture I took way up north. It's not the whale that made the sound that I'm going to play for you. But I'm going to play a sound here for you. And this is a picture of spectrograms operating in real-time hydrophones that we're beaming back to the lab so they can listen to these sounds in real time on speakers at the lab, and they can view the spectrograms in real time. So on these spectrograms, you have frequency on the vertical axis and time. It starts from, this is on the right-hand side of the screen is now, and then it just scrolls off to the left. So it's a couple minutes ago on the other side. And when I play this little video, you'll see it screaming. But you can see that it's close to this hydrophone here, so you get really intense. The color is the intensity of the sound. But you can see in the distance, so this hydrophone is 10 kilometers away, and you can still see that call here. And these other two hydrophones, you can see that call too. So it's really cool that we can see it on all four hydrophones, even though they're 8 to 12 kilometers apart. Now, the reason I'm playing this is because this is such a unique call. This is actually an Alaskan feeding call that was recorded in northern BC. And that's unique because it's never been heard before, and so it caused quite a science stir in the biological community. And so I'm going to play this Alaskan call for you. And they use that call, they use their pectoral fins to sort of scare the fish into a big ball. And they also use the call to scare the fish. But at the end of that call, all of the whales in that group will come up in a lunge and scoop up all the fish in that ball. Well, as many as they can get anyway. And so we'll come back to this a little later in the presentation, and I'll show you a BC call, and you'll see how it's quite different. And the last one in terms of the sort of local sounds is Biggs orca or transient orca whales. And they eat marine mammals. So dolphins, porpoise that you can see down here, seals and sea lions. So these are all these animals, the prey, are smart animals, and they know the difference between the call of a resident orca and the difference between a transient orca or a Biggs orca. So you'll see these dolphins swimming with resident orca, harassing them sometimes. They would never do that with a Biggs because they're prey as far as Biggs are concerned. But Biggs are really smart animals too. Second largest brain on the planet, second only to the sperm whale, and they are smart animals. So they stay silent when they're hunting, and they try and sneak up on these guys, and they'll only start calling after they've made a kill or when they're socializing. Now, this little picture at the bottom here is. I was out with the Straight Watch folks of the CETUS organization, and they monitor the whale watching fleets for make sure they're not violating regulations. And while I was out there, I had a hydrophone with me, so I recorded at the time, and there's 34 of these big orca all gathered together having a real social party. And this is what they sounded like. I'm hoping you guys can all hear that. But okay, so that's the end of the sort of little clips. But animals are not the only makers of sound in the water. Humans generate a lot of sound in the water on purpose. Now, we use passive acoustics, which means we just listen, but we also use active acoustics, which means we pump a lot of energy, acoustic energy, into the water, and we look for the reflections to tell us a lot about what's going on in the ocean. And in industry, I've listed some. It's not a total list, but some of the uses that industry has for generating sound in the water, and some of them are really obnoxious. Like multi-beam sonars can be quite loud. Seismic survey stuff, sonars for national defense can be really obnoxious. Fish finders are, for looking for schools of fish for these commercial fisheries to scoop up. They're quite obnoxious as well. But it's not just industry. On the research side of things, we as researchers use acoustics because it's the best form of energy to use. So we use it a lot too. And we're not particularly nice sometimes. Some of our instrumentation is pretty obnoxious. The zooplankton fish profilers, the acoustic Doppler current profilers, they pump out a huge amount of energy into the sound or into the ocean. Ice profiling sonars, acoustic thermometry and acoustic tomography, it's not done too much. There are systems in the world operating, and they're really quite loud. Seismic surveys for looking at fault lines for earthquake estimates for what's going on below the seafloor, they're really, really loud. So the research community is also guilty of pumping a lot of energy into the ocean as well. On top of that, we have all the unintentional sound that we pump into the ocean as well. So this includes recreational boating, low-flying aircraft, construction, pile driving. That can kill a fish at 10 meters if it's a steel piling. Dredging is and shipping noise. Now, of these, the recreational boating and the shipping noise are the two worst. Now, in terms of shipping noise, we've actually been measuring this for quite some time. And for the first 40 years or so, that the amount of energy that we were pumping into the water just from shipping was doubling every decade. So it was getting really, really bad. And then we started introducing some new technologies, and the sound is still increasing, but it's not quite doubling anymore. I think it was like 1.5 times the last time I looked. But so we've got a long way to go to start curbing this, but we are making some progress. Now, when COVID hit in 2019, a lot of this shipping stopped. And so there was a huge reduction in the amount of noise underwater, which is an excellent opportunity from a science perspective. And there's been quite a few papers published on that. So this graphic just shows worldwide shipping, and the red is really intense areas. Now to look locally, so this is the BC coast. And what you're looking at here, the heat map of shipping density, and this is not the recreational or small fishing fleet. This is only the big AIS equipped ships. This is a logarithmic color scale. So the greens and the blues you don't really have to worry about. But when you get into the reds, that's a very noisy environment. There's a lot of ships operating in there, and the dark reds are even worse. So you're getting into the thousands and hundreds of thousands of vessels per grid square. Now the grid squares are pretty big. They're 5 kilometers squared. But from an acoustics perspective, when we can hear a container ship at 65 kilometers away, a 5 kilometer grid square is actually pretty good size range for us. So that means all of these dark red squares, you're looking at thousands of ships per grid square per year. And so you can never not hear a vessel. So if you're a marine animal trying to make a living in this area and you're relying on acoustics to do it, you're going to have a hard time in this area. And that'll come back to bite us when we're talking about the southern resident killer whale later. So even on Christmas Day, which is the least amount of shipping in the Strait of Georgia, it's just inundated with vessel noise. Oh, I was going to play a clip here. So this is a container ship, and this is what it sounds like to them. Now, it's much, much louder than the clip I was playing because you got these massive, big propellers driving this noise, but you'll get a feel for it at least. Better if you have a good set of headphones on, because then you can really hear the really low frequency reverb on that. But it's pretty obnoxious. So where does all that sound come from? It comes from a lot of sources, really. There's motor generators on the boat. There's refrigerator plants. There's all kinds of machinery operating inside the boat and the engines. But the majority of the noise actually comes from cavitation from the propeller. Now, for those of you that aren't familiar with cavitation, it's the same as boiling water, except when you boil water, you have an ambient background pressure that the water's at, and then you raise the temperature so that the vapor pressure of the water goes above the ambient pressure, and the water will flash to a vapor, so steam, and you create bubbles. Now, cavitation is the same process, but instead of heating the water, you lower the ambient pressure till it's below the vapor pressure of the existing water, and it flashes to water vapor. So it's basically the same as steam, it's a different mechanism for producing it. So in the case of a propeller, here we've got this blade, and it's moving upwards in the water. So as it moves up, this portion of the blade where my cursor is pushing on the water, creates a high pressure, and that generates thrust to push the ship forward. But behind that blade, as it moves up, the water's got to rush in and fill this gap behind the blade. And so it creates a low pressure area. And so in behind that blade, you'll see bubbles form as it flashes into water vapor. And it's really energetic, really, really energetic. And you can see this is a stainless steel propeller down here on the right. And you can see how much it is eroding the stainless steel. So these are really energetic bubbles. And there's millions of them coming off of these propellers. And once it gets into a high pressure regime, once it's away from the propeller blade, now the ambient pressure is higher again, and those bubbles collapse. They implode, and it's like a little miniature explosion. And with millions of these things, it's really, really noisy across a wide frequency range. So here is a spectrogram of a small 18 to 20 foot recreational boat that we happen to record off of Saturna Island. So this is a spectrogram. Frequency is on up here, and time is on the horizontal axis, and the color represents the intensity of the sound. So this is going from 0 to 100 kilohertz, so many times what a human is capable of hearing. Humans only hear from about 0 to 20 kilohertz. For me, it's only 0 to 10 kilohertz, but you can see that the noise from this one small boat covers that full frequency range. Really, really intense down at these lower frequencies where the humpbacks and orca calls are. So this one boat is affecting every marine animal in the area, from the fish and the large baleen whales at the low frequency end, all the way up to the porpoise and dolphins that actually utilize this high frequency bandwidth up here. So even a small boat can have a massive impact on the environment. So that noise has an impact on the animals. For some species, it's been shown that it impedes their reproduction rates. Other species, it impacts on their ability to forage, and I'll talk a little bit about that later. There's two species and two instances where sperm whales and orca actually benefit from that noise, but I might go into that later. But for the most part, it impedes their ability to forage. It can also impede their social cohesion. So these animals are living in an acoustic environment. Some animals like dolphins and orca, different whales, they need to be able to call back and forth to keep their family groups together. If it's too noisy, they can't shout over that din, and they can get separated. That's really bad for family members. Some fish, even commercial fisheries, have been known to displace from areas where there's high levels of noise, bad for fisheries in the area. And some noise, like pile driving and military sonars and seismic air guns, they're so loud that they can cause injury and even death to animals. So lots of implication from the noise of the water. Now I'm going to wind out the acoustic side of things here with looking at two things: echo masking, and echolocation masking, and call masking. So the first one is an example of call masking. And what that is that you've got an animal calling and you've got a vessel in the background, and that animal's having a hard time communicating to other animals because of the noise of the ship. So I'm going to play this clip. There's a container ship 2 kilometers away from the hydrophone, and there's a whale that's calling, and it's half the distance. So it's a lot closer to the hydrophone. You should be able to hear it better. When I play this clip, I want you to see if you can figure out, A, can you hear the whale? And if you can you make a guess at to what the species is?
Yeah, Tom, I think none of the audio you're playing is working.
Oh, crap. That's too bad. Not sure how we're going to be able to fix that in the short term here.
Yeah, no worries, Tom. I think what we can do is potentially layer it over when we post to YouTube, maybe.
Okay. All right. Well, in that case, I'll try skipping the rest of the recordings, and I'll just talk about things. But basically, it's really, really hard to hear the whale call over top of the container ship noise. And so this was a little exercise to do that. The next one I don't have clips for, so it'll be a little easier. So this is echolocation masking. So this is well, it's not actually a southern resident. I just cropped in a picture of an orca here, but so southern residents and northern residents, they eat salmon. And so to find the salmon, they don't use their eyes, they use echolocation. So right behind or down below the blowhole, they generate a click that gets focused through the acoustic lens of the melon in the top of the head. And it comes out like a flashlight beam at about a 20-degree beam angle. And that sound has to spread out through the water column until it hits the salmon. So the salmon, its body is not a good reflector, but inside the salmon, there's a little air bladder. It's about the size of your thumb. And it's a really good reverberator for acoustic sound. So when the sound hits it, it insonifies this little air bladder, and it reverberates and it radiates sound in all directions. And then that sound will travel back to the whale, and it'll pick it up through its jawbone and into its inner ear. And all of that is governed by the active sonar equation. And I won't go into all the details of that, but it's a very powerful tool for estimating the ability of military sonars or even whales to echolocate. So if we think of this salmon at 200 meters away, he's making a click, like the snapping of your fingers, and it's trying to listen for the echo from this thing that's the size of your thumb 200 meters away. So the energy that comes back is very, very small. If there's a lot of noise in the background, he's not going to hear that echo, and he's not going to get his lunch. So what you can do is you can look at the in the literature, and you can find all of the different parameters in the active sonar equation, and you can estimate how well an orca can detect this salmon. So if there's no vessels in the area, that's this green line here, and it's really quiet conditions, no stormy weather or anything, it's going to be able to detect that salmon out to about 200 meters. And because it's a flashlight beam going out at about 20 degrees, it means he's insonifying about 256,000 cubic meters of water with that click. And if you look at drone footage, that whale from the top, you'll see those whales, they'll point their head down and they'll sweep their head back and forth, pointing that flashlight beam around looking for salmon. So if we say in pristine conditions with no noise, that 256,000 cubic meters of water is their best conditions. That's 100% of their ability to find salmon. Now, if we bring this particular boat here, which is a whale watching boat, and at 7 knots, it's generating 140 decibels within the echolocation bandwidth of the whale. You can add that to the background noise, and that's going to reduce the detection range to about 150 meters, or about 110,000 cubic meters. So at a kilometer away, operating very slowly, they've already reduced that whale's ability to find fish by about 42 or 43%. Now, our regulation, and these guys, the whale watching fleet, they have their own rules that say once they get to within 1,000 meters, you must slow down to at least 7 knots, which is great because they're way noisier than that above 7 knots. The regulation is 400 meters away from all of the whales, unless you're a licensed whale watcher and it's a transient, then you can go within 200 meters. But at 400 meters, this particular boat operating very slowly, it creates so much noise at the whale's location that it reduces its searchable volume to about 40,000 cubic meters of water. So now they're down to about 16% of their ability to search the water column for salmon. Now, there's not a lot of salmon in our area anymore anyway. It's really been with the dams and stuff impeding the reproduction and the overfishing. There's not that many salmon left. And then you factor on top of that these whales are followed around by these boats all the time. It's really hard for these whales to find salmon now. Now, Lance Barrett Leonard has done some surveys of this, and he estimates that in the southern resident population, 50% of the whales are malnourished. And this is a big reason why. Part of it's the salmon not being there, and part of it's their inability to find them. Okay, so what else can sound tell you? And this is from a human perspective now. So if you see in a spectrogram a curve like this little bathtub type curve, it's actually called a Lloyd's mirror, and it's caused by the constructive and destructive interference of the direct path from the propeller to the hydrophone, and a longer path that goes from the propeller up to bounce off the surface and down to the hydrophone, and it creates these constructive and destructive interference patterns with frequency. And as the boat approaches the hydrophone, gets closer and closer, it gets tighter and tighter spacing in the frequency of this pattern. And then as it goes away again, it opens up again. So we know that the vessel pass, that this is a boat. Nothing else creates these kinds of patterns in the water. So it's a boat going past the hydrophone. And where it bottoms out here, that was the closest point of approach to the hydrophone. So just at a glance, you can tell, yep, there's a boat there. And at 21:45 and 30 seconds or 20 seconds, that was at its closest point to this hydrophone, just at a glance from this spectrogram. And this is going up to 25 kilohertz. Now, if we focus in at the very low frequencies of this, we can learn even more. So here's the Lloyd's mirror out the other end. We're only looking from 0 to 130 hertz here now. But there's a bunch of these monotonic tones coming out. So there's a 60 hertz tone, there's a 20 hertz tone, there's a 10 hertz tone, there's another one 3.3 hertz below that. We can look at these and say, yeah, as long as there's no hydrophone self noise on the system, we can look at this and there's a 60 hertz tone there. That's a motor generator package generating electrical power for that ship. And it's probably coupled directly to the hull because it's a really strong line, which means this is an old boat because it's bolted straight to the hull. There's a bunch of lines down here, and we can look at this and look at that 20, the 10, and each of these 3.3 lines that are there. And from that, I can say, yep, there's 2 propeller shafts on this boat, and there's 3 blades on each propeller. So this is a big old boat with 2 blades and 3 blades on each of the 2 propellers. And looking at the frequency here, we can say, yep, the RPM of those shafts is 200 RPM. And for that kind of large vessel with 2 shafts like that, normally 10 turns per knot. So the boat is probably traveling at about 20 knots. And so this has got to be, since this is at East Point in Boundary Pass, it's a pretty confined area. The only boats that travel at that speed through this area are car carriers and container ships. So we can tell a whole lot just from this. The whales are even better at this. A sperm whale at 10 kilometers away can tell the difference between different types of boats and long liners that are putting gear down or just waiting around, to long liners that are actually hauling up their gear. And they will make a beeline for a long line vessel that's hauling up its gear, because they can pluck the fish off that line. So they're even better at it than we are. A good acoustic analyst will tell you whether there's 1 or 2 diesel engines on this vessel. They'll tell you how many cylinders are in the diesel engine, whether it's got a reduction gearbox between the engine and the prop. And a really good analyst will tell you how many teeth are in the gears of that reduction gearbox. It's astounding what some of these military acoustic analysts can tell you about a vessel. Okay, I'm going to switch gears here now and do a little bit of an overview of the Pacific Coastwide Hydrophone Network. So north is not straight up and down on this map. I kicked it over just to make it fit on the screen a little bit better. So we've got the whole BC coast here from the southern tip of Vancouver Island all the way up to almost up to Alaska. And the hydrophone network has hydrophones in its partners distributed throughout the whole region. Strait of Georgia is a very, very important body of water. There's a lot of people living in this area, using it for recreational fishing, for boating and such. Canada's largest port is in the area. One of our most productive rivers, the Fraser River for salmon, is in this area. It's a very, very important body of water. And there's 2 choke points here, one at the southern end, Active Pass and Boundary Pass, and then Johnson Strait at the northern end. And so those are really good areas to study, because all of the water that flows in and out of here with the tidal cycle has to flow through these choke points. All of the vessels have to go through those choke points, and all of the whales have to go through those choke points to get in and out. So very important areas to monitor. So the Saturn Island Marine Research and Education Center, they have 4 hydrophones here in Boundary Pass. Transport Canada has a bunch of hydrophones in there. Department of Fisheries and Oceans has hydrophones in all the Gulf area here, and even in Juan de Fuca. Orca Lab has been operating listening to whales for about 50 years. They've got 7 hydrophones in the area. There's 4 in Johnson Strait and 3 in Black Knee Pass here. And so they do a fabulous job of monitoring that area. On the central coast, in all these fjords here, the whales, like humpbacks in particular, but even fin whales in some cases, they use all these fjords to forage, like all the way up here near Buttedale. This is way inland, and I was up there a few weeks ago and working on the hydrophone here, and there was 10 humpbacks right in front of me feeding. Pretty spectacular. So we've got a few Jasco hydrophones and a few Ocean Sonics hydrophones in this area that we've put in. And then there's the big 4-element array that I'll come back to in a sec in Squally Channel up in Gitgat territory near Hartley Bay. So that's sort of the coverage of the hydrophone network. The systems that we put in look like this. And I apologize for my cartoon here, but best I can do. So we've got these moorings here. These are folding moorings so that we can, it doesn't take tools or anything. You can just pop off these cross braces that lock everything in place. So when we go out in a small boat, we can fold these things up so we can take 2 or 3 of these on the boat with us. And we can lower them down with a rope to the seafloor. And then we can recover them using an ROV or divers to hook a rope onto. So what we have here in this cartoon is we've got this mooring sitting about 20 meters below the surface. And we need to get at least that depth so that the wave noise doesn't influence the hydrophone too much. And then we've got a cable coming up here to shore to our box. And here's an example of one of the small boxes. It's got a bunch of batteries in here, solar panels up above it, charger. And this particular box is outfitted for an Ethernet radio bridge back to the lab. So this black box is an Ethernet switch, but sometimes we'll have a big data logger box mounted in there too. So that's what the system looks like basically at each of the sites. And when we're recovering one of these systems, we typically use the ROV to do this. Because A, there's a lot less risk than paying for divers with all of the liability that entails and the expense that entails in getting commercial divers up to an area. Some areas we can get access to science divers, which makes it a little cheaper. But the ROV, it's just a small little ROV, and we've custom designed this little mandible, we call it, for it. And so Jeff's piloting this. This is not one of our acoustic arrays. This is just a little test jig, but it shows you how we go about doing it. And we've done this so many times that this ROV has paid for itself several times over. So here's Jeff going to fly in, and he's going to attach this rope on the left here to this lifting ring here. So he's just got to get one of the tines of that mandible into that lifting ring, and then he can lock the rope on, and then he can back away, and the rope is hooked onto that mooring. And then typically this rope would go up to the boat, and I'm normally standing up on the boat. So Jeff will take a look at this thing and make sure that that rope is hooked on, and then he'll back the ROV away from the mooring. And then once he's sure everything's going, he'll come out from underneath his blanket that he uses as a sun shield, and he'll tell me to lift it up to the surface, and he backs out of the way. So when I do this, and then I'll lift that mooring up just as I'm doing to that little jig right there. So that's how we recover these things. Now, if we put out more than one of these things, we can actually localize where whales are in the water. So here's another little cartoon. We've got a lab up in the top right. This is what the shore station sort of looks like with Jeff working on it. Hydrophone there. 10 kilometers away, we have another remote shore station with a hydrophone system. Way down here, we have another hydrophone with a remote system. And these two radio their signals back in real time to the lab, so that you can hear all of the hydrophones over the speakers, or you can watch the spectrograms in real time. So if we have a whale at one location or another location, and it makes a call, it takes a certain number of seconds for that sound to reach each of these three hydrophones, and it's different depending on where the whale is. So, for example, this whale takes 3 seconds to get to this hydrophone. This whale takes 10.5 seconds, and it's different for each hydrophone. So based on that difference in time, we can actually calculate where that whale was when it made the call, which is really cool. So this little presentation here, this is Ben Hendrick's software. He has Sound Space Analytics, and we're using his software to do this analysis. You'll see the date. When I play the movie, you'll see the date here and the time here, and it'll scroll through, and you'll see his call detections. Now, he doesn't plot every call. He only plots clusters of calls in order to have a higher reliability that, yes, that is an actual set of calls. But watch where these things show up in here. And at the lab, you can see this in near real time with only a couple minutes lag. And he has a dashboard set up so you can see historical stuff on this too. Now, this is only fin whale 20 hertz calls. There's fin whale 40 hertz calls. There's humpback feeding calls and social calls and orcas and stuff. But this is just the fin whale 20 hertz calls. So it's pretty cool to be able to, watch that whale track around through this area. And that's really cool because, because you can actually tell some of these biologists to say, hey, there's a whale out there, it's over in this area, get your cameras ready. And so it's really neat. I'll show you a little video of that in a second. This is some of the other stuff that Ben puts up on his dashboard. There's many, many different data types that he puts onto his dashboard. And in this case, we're just looking at sound pressure levels over the entire year. The dark one is a month, 30-day average, and the light green is a 7-day average. So you can see that every 2 weeks, the tidal variations with tides flowing in and out, and the implications of flow noise, as well as the implications for wind versus the tide generates higher waves. You can see winter storms are noisier. You get into summer, it gets really quiet. In 2021, we had a more no cruise ships, or a lot of the big shipping was not present, and so it was nice and quiet. And then all of a sudden that moratorium was lifted, and all of a sudden you see a huge increase in the noise as those vessels started to transit in through the area again. And this is one of his plots that I really like. Well, there's two of them here, but they're the same sort of thing. The top one is clusters of calls of orca, and the bottom one is humpback whale moans. So not their calls or not their feeding calls or their social calls, just the moans. And each one of these is a cluster of call. He doesn't plot single calls. But in the dashboard, you can hover over one of these points and it'll pop up a little window and it'll say, for this little point here, there was 132 calls within 51 minutes for that cluster. And so over the course of the year, you can really see, are they, this black line is sunrise and this one is sunset. So you can see, are they utilizing more of the nighttime versus the daytime, and what time periods of the year are they utilizing this particular fjord? So pretty cool plot from that perspective. The last slide for this presentation here is an example of bubble net feeding. So in this case, we're listening to the and viewing the spectrograms in the cabin, the research station, and so we know there's whales foraging in the area. The drone goes up in the air. People all pour out onto the deck with their cameras, and you can listen to the calls. And when the bubble net feeding call stops, you know those whales are on their way to the surface. And so you can tell the biologists that before the whales even hit the surface, and they can have their cameras pointed at the area and ready to click. It's really, really changed the way we do studies in the area. So here, this is 12 humpback whales all feeding cooperatively. Now you won't be able to hear the sound, unfortunately, but so there's the cabin, and this ring in the middle here, that's the bubble net, and the whales all coming up to the surface to feed. And this is such an active area for whales, for fin whales and humpback whales. We've been standing on the deck of that cabin and having whales feeding in singly and in groups 5 meters from shore. You're just looking down off the deck right into their nasal passages. It's incredible. Oops. Okay, so that's the end of the formal presentation. Whoops. I wanted to make two last shameless plugs here. One is we're all interested in ocean equipment, ocean engineering, ocean science. So this is a good group to sort of pitch the IEEE Ocean Engineering Society to. And for those of you that aren't members of IEEE, I would encourage you to become members. There is an annual fee for it, but it does give you access to a huge network of people and networking opportunities. And it gives you access to a lot of papers and things that you can access if you're a member. If you're interested in joining IEEE or even more so the oceanic engineering portion of IEEE, you can give me a shout and I'll help set you up that with a referral. And the second plug is for a UVic evening on the 6th of December from 4:30 to 6:30 in the engineering lab wing at UVic. So there's 25 different ocean engineering problems that industry has identified, and they were handed out to the students, and they chose some of the projects or some of these problems to try and come up with solutions for. And they're going to be presenting those on the 6th of December at UVic. So I would encourage all of you to come out. I think you'll find it very entertaining. And we as the Ocean Engineering Society, we actually coughed up 4 sets of first, second, and third monetary prizes for the students for this, $300, $200, and $100 each. 3 of the sets will be presented on the 6th of December. And if you want to register ahead of time, you can through Eventbrite here. You can do a screen capture right now if you want that address, or you can email me and I'll send it to you. But yeah, it should be fun, and there should be some interesting solutions, both hardware-wise and user interface-wise, for ocean industry issues. And with that, I'm going to finish off and just give you our contact information if you want to send us any requests for any of that information, or just ask questions. And
Thanks
back
so
to you.
much. Yeah, that was amazing. I know we usually like to keep it to 5, so if anyone has to jump out, no worries. But otherwise, we'll just go to questions.
Yeah, sorry, I got a little verbose there. Went over time.
No worries. I didn't see any hands come up, so I will ask one, and mainly about sperm whales. I mean, I had no idea that we had sperm whales in the area. So, I mean, how are they doing? Are they, is the population doing okay?
I'm a physicist, not a biologist, so not really the person to be asking that. But as far as I know, they're doing all right. But you know, I really can't honestly answer that question.
Right,
I
fair
know
enough.
that they're you hear them all the time on the Ocean Networks Canada hydrophones out in especially around Barkley. So they seem to be doing well there. And it's nice that we had a whale actually come in and circumnavigate the island. So I think that's a good indication.
To Daniel.
Danny, come on.
Hi. I was wondering, since you're a physicist, are there options to reduce the noise from the same vessels?
Yes.
Are there low-hanging fruits?
Yes. So the Transport Canada has actually done a lot of work on that through the Port of Vancouver and their ECHO program. And the ECHO program has all kinds of stuff online at the Port of Vancouver, and you can go and read through some of it and see some of their science papers and stuff. It's really quite good. But they've done a bunch of different studies on reducing transit speeds of the vessels, and that reduces the noise a lot. It prolongs the noise, but at a much lower level. And so that's made quite an impact, and they're doing that every year now. They've also put in sanctuary zones for the whales in certain areas where they know the whales forage, to move the vessels away from those areas. So that's easy, low-hanging fruit as well. And the other thing is there's a lot of military technology that used to be top secret back during the Cold War when I was in the military that is now public domain. And the military has been pretty good about pushing some of those technologies out into the civilian world in order to try and quiet some of these vessels. And Maersk, the largest shipping company in the world, they took out one whole class of their vessels, outfitted them with a bunch of different technologies to make them quieter. But as a result, they actually improve the efficiency of those vessels because they're not wasting all that energy making noise. So they've reduced their gas consumption and made the ships better for the environment. So Canada Shipping Lines, Maersk, there's some shipping companies that are really stepping up to the plate. BC Ferries is really stepping up to the plate too. So yeah, there is a lot of progress on different propeller designs and shrouds and vibration isolations and stuff for the ship.
Very, very interesting. Are you aware of if there are any fee differences in the area around Vancouver Island, where larger ships have to pay higher fees?
Yes. So, well, yes and no. So the Port of Vancouver is leading the world on this, and many countries around the world are actually watching, including the U.S., watching what Port of Vancouver is doing. And they have a program that they're sort of trialing that allows the quieter ships, because they're monitoring these ships' noise levels as they come in. And the quieter ships, they have an incentive program that will allow them to jump the queue to get into the berth quicker. And it's very, very expensive for these ships to hang around doing nothing and just anchor waiting for some berth time. So if you can jump that queue, you can save yourself hundreds of thousands of dollars. And so, yes, there are incentive programs being trialed out there, and I'm hoping that's going to make a big impact in the long run.
Cool
Thank you.
question.
Very interesting. Thank you.
Maybe just time for one more question if anyone's got one. Ray Z.
Okay, thank you, Tom. It's a fabulous presentation. My question is, I saw that the frame, the mooring seems very small and easy to take.
Yeah.
The frame and the mooring, is it? When you deploy it, I guess you need to do something to make it very firm on the sea floor to avoid any noises from the shaking or moving by the current. So
so there's a whole bunch of things in the design there, Ray, for doing that. So on those ones we attach halibut flagpole weights onto them. They're 26 pounds each, and we put 3 of them on there. So they're nice heavy platforms. When we put them, they don't move. They can handle up to 5 knots of current, and they won't move. What we have found, though, is that even in the interim sanctuary zones where you're not allowed to bring your boat into, that people will still go in there and fish, and those great big salmon hooks will hook onto the mooring. And we've had 4 times now a mooring has been hooked and brought flipped over, or in one case brought right up to the surface. The guy takes his hook off the thing and then throws the whole thing back into the ocean, and it landed upside down on the hydrophones, each of the hydrophones being $10,000 each. So very, very expensive hit, and we've had that happen a few times.
Yeah, thank you. Very interesting.
Good question, Ray. Tom, thanks so much. Yeah, I guess what we'll try and do is we're going to post this to our YouTube channel, and we might try and add some of those sounds. So if folks,
I can send you the whole thing if you want.
Yeah, I know that'd be helpful. But I guess we will say bye for now, everyone, and have a good Christmas break. We're going to take a break in December, so we'll see everyone back in January.
Okay,
Thanks,
Dustin.
See you later.
Bye, guys.
Nice to see you again, Tom.
Awesome.
Yeah,
Thanks, Tom.
yeah, thanks,
you.
Ray.
Bye all. Good to see you.
Bye, everybody.